Hi, my name is Harish Gundapu. As a part of my course, I am doing this presentation. This presentation is based on the optimization and learning algorithm for stochastic and adversarial power control. When we consider a wireless network system, power source is one of the main concern problem because in wireless communication systems, we may have portable devices which can carry a limited amount of load. And if the network is idle, means it is not working, or if the communication doesn't happen, then we need an optimization power control so that to avoid wastage of power. So in this presentation, I'm going to explain how we can deal this problem and how it can be made automatic. It means the switching from full power to optimization power can be done automatically based on the network behavior. Actually, I am presenting a research paper based on this. So let's get into the problem statement. As I have said, power control in wireless network is one of the main concern problem. Recently, it is demonstrated that significant throughputs can be achieved using data-driven online learning algorithms supported by cloud computing architecture. In this paper, others have provided theoretical guarantees for such type of algorithms. The authors have solved two problems in particular. The first one emphasizes on large term throughput. This problem reduces to solving convex optimization problem with noisy stochastic measurements. Second one emphasis on robust short-term throughput. This is an online optimization problem where an adversarial chooses the reward function. The authors have solved these papers using stochastic and online gradient descent methods, which are customized for problem optimization and establish their convergence analysis. Always, the power control has been a major issue in wireless network and cellular communication systems. For better and efficient transfer of data, a lot of power is required. But always, there is a trade-off between the rate of data transfer and power consumption. If we want high throughput, then even increasing the number of antennas will serve the purpose. But still, it also uses power. The main problem in power control in recent or modern wireless networks like LTE systems is the primary source of interference, that is intercell interference. Not only that, the interference pattern keeps changing at each time slot. So the learning algorithm should be fast to analyze the interference. In this paper, authors try to solve the maximization problem of cumulative utility of different users in a wireless network using online-based power control. The authors tried to solve this problem in two different scenarios. The first one is considering the problem as the utility maximization of the average log signal to noise ratio. The second one is considering robust short-term performance similar to LTE like wireless network setup. For each scenario, authors have considered two different cases, general power control and fractional power control. The main contributions of this paper is formulated the average SINR based optimal power control problem as a convex optimization problem, proved that SGD based algorithm converges to optimal power control policy. They have presented the online gradient descent based algorithm for robust short-term performance. First, let's see SINR based general power control. Here, the problem formulation is given like this. These are the notations just to know uh, which variable corresponds to what. It is formulated as maximization problem, utility maximization problem. Here you can see this is a utility maximization problem, as we have earlier said. At any instance, they have given the utility is log of 1 power e power psi I. To convert this into convex optimization problem, affine inequality is applied. Now the convex optimization problem will be like this. So the overall convex optimization problem is minimum of this. Algorithm analysis. The authors prove that there is a solution to solve convex optimization problem. They have designed the algorithm based on stochastic gradient descent algorithm. They have taken many lemmas. I may not be explaining the complete proof, but I will give an overall idea what these lemmas are. Let's see the first lemma. For the convex optimization problem, there exists a non-empty, closed and bounded set of optimal solutions. So here they have taken S is equal to gamma comma Q. From the constraints of convex optimization problem, if S tends to infinity, then either Qi or gamma I tends to minus infinity for at least some I. Then the problem will be like this. Lemma 2. For the primal and dual optimization problem characterized by Lagrangian function and strong duality holds. Lagrangian function is applied to get the optimized values. This is the Lagrangian function and this is the optimized value. And to this optimized value, Slater's conditions are used. Lemma 3. This looks pretty big, but I will explain it in a short way. Here the authors want to prove that this is a non-empty bounded closed convex set and it can be computed by using the previous lemmas. And they have given that M is the upper bound on variable Qi for all I, and H dash is a vector comprising upper and lower bounds on the random channel gains for all the users in the network. Gamma dash is a vector comprising upper and lower bounds on the noise variance in all the cells. X dash is the vector comprising upper and lower bounds on the probability that a user is on at any time slot. Here KKT conditions are used for the previous results to get the bound on the optimized value. And in lemma 4, they have applied Lipschitz continuous on set psi. In this lemma, the continuously differentiable function L and psi is a non-empty bounded closed convex set. Both these statements are used. Now the stochastic gradient descent power control algorithm is used. The algorithm goes this way. First they are initializing Z, which is psi, and they are for time t is equal to 1 to n, this loop runs. First, they are applying Lagrange's function and finding the optimized value. Then they are finding z. Now theorem 1. After t iterations of SGPC SINR algorithm, we have expected value of epsilon of t is equal to closed function of maximum of theta comma theta inverse dψg by root t. The SGPC SINR algorithm converges to the optimal solution as this. The implementation of the power control algorithm requires various channel gains. The theorem 1 implies that the total expected regret up to time t is given by this. Now let's consider the second one, SINR based fractional power control. The problem formulation is this. Fractional power control is method of power control used in LTE systems. The power assigned to user I is given by this. FPC reduces the number of free parameters when compared to GPC. FPC means fractional power control. GPC means general power control. In GPC, each user can have its own power assigned, which leads to the optimization of large number of parameters. In FPC, each cell has only two optimization parameters. But the GPC's performance is always better than FPC as the GPC is more general. The optimization problem of FPC is this. Here all the notations remain same as that in GPC, which we have earlier showed. Algorithm and analysis. Similar to that of GPC, first we have a lemma which is presented to prove that the solution exists for the optimization problem. Then some properties of optimization problem, and lastly applying the gradient descent algorithm. Lemma 5. There exists a non-empty closed and bounded set for optimal solutions for the FPC optimization problem. Here we are showing that always there exists a non-empty closed and bounded set of for optimal solutions of FPC optimization problem. For primal and dual optimization problems characterized by Lagrangian function holds strong duality property. Previously we have applied Lagrangian function to get the optimized value. Here also we are using Lagrangian function and we are obtaining the optimized value for it. And after that in lemma 7, in this lemma the properties of Lagrangian functions are proved similar to that of GPC, which we have shown previously. Lemma 8. Here we are applying Lipschitz continuity on the set psi. The algorithm for FPC is, here also we are initializing Z, which has two parameters. Here Z indicates a cell and it is running for t is equal to 1 to so on n, and we are computing the optimized value and we are computing Z. Theorem 2. After t iterations of SFPC SINR algorithm, we get expected of psi of t is equal to function of maximization of theta comma theta inverse d psi g by root t, similar to that of GPC. And this algorithm solution converges to optimal solution as this. Now let's see the second problem, robust short-term performance. The problem statement is, in average SINR based utility maximization, the focus is on achieving good long-term performance. But here, the authors want to provide good short-term performance which is robust to channel state statistics. The utility problem of each user is formulated as a function of their instantaneous throughputs and no assumptions on the channel state statistics. In machine learning literature, the quality of an online algorithm is measured by comparing its performance with the performance of an algorithm which knows the future channel states but is only allowed to choose a time-independent power sector. Here also, all the notations will be same as that of the previous one. Here, the instantaneous logarithmic SINR for user I at time I t is, they assume that there is an upper bound P max on the power assigned to any user. The instantaneous throughput for user I at any time t is this. By using the log utility function, the cumulative instantaneous utility of all users at time t is the summation of all. Here W is a weight factor associated with the user utility function of user I. To optimize the short-term performance of the network for t time slots, we need to solve the following optimization problem to compute the best time-independent power assignment P is minimum of summation of negative of this quantity. This is a concave function and the negative of it will give convex function and it is a decreasing function. As long as this is concave, then the negative of logarithmic of this value will be always convex and the resultant problem will be an online convex optimization problem. Now let's consider general power control. Here also the same transformations that are applied to the previous problem will be followed. The instantaneous logarithmic SINR for user I, we get this. And similarly, it is computed for fractional power control also. Using both the transformations GPC and FPC, we can get the online convex optimization problem with respect to the power control parameter Z. To measure the performance regret matrix is used. The regret is defined as like this. Now let's see the algorithm. Here online gradient descent algorithm is used and f is continuous and differentiable on set psi and this set is closed, bounded and convex. And here glibs function is used. Algorithm 3. Online problem control for robust short-term performance. Here Z is initialized and loop is run for t is equal to 1 to so on n, and they are computing the minimum value by using Lagrange's function, and then they are computing Z. For OPC, online power control, RSTP algorithm. Online power control for robust short-term performance algorithm for any time t greater than or equal to 1, we have regret as this. Function of t regret implies that the average performance of OPC RSTP is asymptotically as good as the best expert in optimization problem. Therefore, OPC RSTP is both online and efficient. Conclusion. In this paper, the authors considered the control, optimal power control problem in modern wireless networks. They have presented SGPC SINR and SFPC SINR learning based algorithm for SINR based utilization maximum problem using general and fractional power control. They have also given OPC RSTP online algorithm to achieve robust short-term performance for both general and fractional power. Now, if we see the overall content of this, apart from the mathematical terms, first what they have done is they have identified the utility maximization problem, and they have converted the convex problem to a concave problem to a convex utility maximization problem, and then they have applied Lagrange's value to get the minimum or the optimal value, and from there they have used KKT conditions and got the optimal solution. This is how the algorithm for all these four methods have been done, but based on the problem, uh, the the calculations and the variables may vary, but the overall algorithm goes like this only. Thank you.